What is a halide? Now, a halide compound will contain a halogen and another element. Now, that other element is usually a group 1 or group 2 metal. We consider hydrogen to be in group 1. Although it's a gas, it is still in group 1 because it has 1 electron in the outer shell. So a halide is a compound where one of the elements is from the halogens, and the halogens is in group 7, and it is chemically combined with another element which is in group 1 or group 2, and hydrogen is in group 1. Now you can have silver chloride, and that is also a halide. It's a metal and a group 7 element. Let's have a look at this chemical reaction. You've got chlorine plus sodium bromide. That produces sodium chloride and bromine. Why does that happen? Because chlorine is more reactive than the bromide, the bromine from the bromide. If you look at this, if you look at the group 7, so you've got fluorine, chlorine, bromine, iodine, and astatine. The further up you go, the group 7, the more reactive it is. So fluorine is the most reactive, and astatine is the least reactive. So bromine is more reactive than iodine, chlorine is more reactive than astatine. So because chlorine is more reactive than bromine, I was going to say bromide, but I just changed to bromine. So if chlorine reacts with sodium bromide, because the chlorine is more reactive than the bromine in the bromide, it displaces the bromide, and then the chlorine will attach itself to the sodium, becoming sodium chloride and bromine. Okay, let's have a look at this equation here. So you have Cl2, which is diatomic. Now the reason why it's diatomic is because if we look at this diagram here, so in this diagram you've got 7 electrons on the right hand side, the one with the blue dots, not the crosses. So the one with the circles, it has 7 electrons in the outer shell. The one with the crosses, it's got 7 electrons in the outer shell. However, let's just say that you put the 2 chlorine atoms together, you end up with sharing the outer shell, and then you end up with 8 electrons in the outer shell, 8 electrons in the outer shell for both of them. So here you have a full outer shell only when you're sharing them. And that is more stable than if you had just a single chlorine atom. So this is a covalent bond when they're sharing electrons. It's covalent, it is not ionic. Alright, so now that we know that Cl2 is diatomic, all the halogens are diatomic. Also, you've got hydrogen and oxygen, they are diatomic. So Cl2 as a gas plus 2 moles of sodium bromide, NaBr aqueous, that produces 2 moles of sodium chloride aqueous plus Br2 diatomic bromine gas. Aqueous in solution. So, so why is it NaBr? Because sodium will form +1 ions, and bromine will form bromine -1 ions, and they will naturally combine. Similarly, for the sodium chloride, the sodium will form +1 ions, and the chlorine will form -1 ions, and they will naturally combine. You don't need 2 atoms of chlorine to balance out the sodium, because you've got +1 and -1. They will, when they are together, they will naturally neutralize, becoming a neutral charge. Right, so chlorine plus sodium bromide, that will produce sodium chloride plus bromine, because chlorine is more reactive than the bromide, the bromine in the bromide. The chlorine will displace the bromide, and then the chlorine will attach to the sodium, becoming sodium chloride plus bromine. So a more reactive halogen will displace a less reactive halogen. Now bromine is a liquid at room temperature. It is red. However, it could be reddish, but yeah, so it could be reddish brown. It is a liquid reddish brown at room temperature. It is toxic. So bromine is a toxic liquid. However, if it gets really hotter, so as you increase the temperature, it becomes a gas. It becomes a reddish brown gas. In solution, it becomes orange. It becomes orangey brown. Have a look at this slide and complete the sentence. So the one with the circles, there's a missing word, and you have the missing words underneath. The answers are here. Have a look at this question. So I'll read it out and then I'll show you the answer on the next slide. Which one of the following statements about... Alright, let me read it out. Which one of the following statements about elements in the periodic table is not true? So not true. So A, Group 1 elements are metals. B, Group 1 elements are stored underwater. C, Group 0 elements are gases. D, Group 0 elements have outer full shells. Question 2. Which one of the following statements is correct? Group 7 elements are able to form positive ions. B, chemically unreactive. C, non-metals. D, harmless to human health. 3A, iron is a typical transition metal. State 2 physical properties of iron. Right, these are the answers. Have a look at the answers. The answers is B for number 1, C for number 2. For 3A, you can say high density, high melting point, very hard. But in the extra information, it does say ignore properties of iron compounds. B, the Statue of Liberty has an outer coating of copper over an iron frame. It has been exposed to the corrosive atmosphere for many years, but the copper has only turned green on its surface. What does this suggest about the reactivity of copper? 4. Iodine is found in group 7 of the periodic table. It is a shiny, near black liquid. What is the formula of an iodine molecule? Iodine is a solid. It's a black solid, not liquid. I said liquid. The chemistry of iodine atoms is determined by the number of electrons in their outer shell. How many electrons do iodine atoms have in their outer shell? So it is unreactive. The formula is I2, and there are 7 electrons in the outer shell. Iodine, like all the elements in group 7, can form ionic compounds when it combines with sodium metal. The formula of sodium iodide is NaI, suggests the formula of sodium bromide. What is the formula of an iodide ion? Part 3. Compounds containing iodide ions are found in seawater. Iodine is obtained from seawater commercially. There is a lot of salt in seawater, and it's mainly sodium chloride. Give the name of an element that could be added to seawater in order to obtain the iodine. What general name is given to that type of reaction occurring between the elements you suggest and iodine ions? Elements added, type of reaction. Question 5. The group 1 metals, sodium and potassium, are often reacted with water in laboratory demonstrations. Give one similarity and one difference that you would observe in the reactions of sodium and potassium in water. So similarity is, difference is. And B, name the solid formed when sodium reacts with water. Alright, so the answer is sodium bromide, NaBr, and I minus is chlorine, and its displacement, except fluorine, except redox, marked independently. And the similarity is that both will move or float around the surface, fizz, catch fire, melt. The difference is that potassium will react more vigorously, bubbles given off faster, or it will start spitting. And 5B is sodium hydroxide. Let me just quickly go through NaBr. Remember I said NaBr because sodium is a +1 ion, bromine is a -1 ion, they just combine. The iodide ion is when the iodine gains 1 electron, so it has extra electrons, meaning there's more positive. I mean more negative. I said positive. It should be more negative because there are more electrons. And in this case, there's an extra -1 charge. And for chlorine displacement, because chlorine is more reactive than iodine, you can use a displacement reaction. So because chlorine is more reactive than iodine, it will displace it. You can also say fluorine, but because fluorine is more reactive, and it's just better to use chlorine. But fluorine is more reactive and it will work. So anything that is a more reactive halogen will displace a less reactive halogen. Give a reason why group 1 metal rubidium is not demonstrated in the classroom reacting with water, because it's too violent or dangerous. 6. Right, so the table below shows the results of the reaction of 4 metals with water and steam demonstrated by a teacher. So you've got 4 metals, W, X, Y, and Z. For W, there is no reaction with water or steam. for X reacts rapidly with water releasing bubbles, the reaction with steam was not attempted. Y, little reaction with steam, the hot water slowly reacts with steam, very slow reaction with water, the hot metal reacts vigorously with steam. So W, X, Y, and Z are not the symbols for the elements. Name the gas produced when metal X reacts with water. Suggest the reason why the reaction of metal X with steam was not attempted by the teacher. C. Place the metals in order of chemical reactivity from most reactive to least reactive. What would you expect to see if the metal Z was added to a solution of the sulfate of metal W? Explain your answer. So I'm going to show you your answer next. So the answer is that it is hydrogen gas formed. 6b, it is too dangerous, likely to explode. So the most reactive is X, then Z, then Y, then W. For 6d, Z would disappear. Metal W would come out of the solution, precipitated out. Z is more reactive. It displaces W. Right, for this diagram, this just shows why the bromine is diatomic, because if you have 7 electrons in the outer shell, compared with this configuration, because here you have a full outer shell now. If you're sharing with another bromine atom, you have a full outer shell, but if it was just on its own, then it would just have 7. Okay, so the chlorine pushes out the bromine in the bromides because chlorine is more reactive than the bromine in the bromides. The chlorine pushes out the iodine in the iodides because the chlorine is more reactive than the iodine. Okay, so just a quick recap on the halides. What is a halide? Remember, a halide is a group 7 element plus a metal or hydrogen. So an example of a halide, you've got hydrogen bromide. Another example is sodium chloride. Now, halide ions are negative because they are in group 7 and it needs that extra electron. When it gains that extra electron, it becomes -1. So halide ions are fluoride, F-, chloride, Cl-, bromide, Br-, and iodide, I-. We can identify halide ions by adding nitric acid and an aqueous silver nitrate solution. Each halide ion gives a specific specific colored precipitate. Okay, so let's have a look at this one. So you've got chlorine diatomic chlorine adding 2 electrons, and that becomes 2 Cl-. Why is that? Because it's being reduced. Remember, oil rig, oxidation is lost, reduction is gained. So if you have a diatomic chlorine and that gains 2 electrons, remember you need to have a full outer shell. Once it has that full outer shell, then you have 2 separate chlorine ions. That's what it means. So it's reduction because it has gained an electron. So the Cl2 is a diatomic chlorine, and once it has gained an electron, the 2 chlorines, because they're already joined together, it becomes 2 separate chlorine ions. For oxidation, because on the left hand side you've got 2 Br-, it is already ionized. It is already an ion. So because it's already an ion, it's either lost or gained. In this case, the bromine has gained an electron, that's why it is negative. And then if it loses an electron, then it becomes diatomic. So in this case, you've got 2 separate bromine ions. They lose an electron. Once it loses an electron, it becomes diatomic bromine and 2 electrons. All right, so what are the chemical properties of transition metals? So I went through that question about the transition metals. The transition metals are usually harder, they're usually more dense, they are usually less reactive than group 1 or group 2 metals. However, you've got iron, because iron is reactive, but it does react very slowly with water and oxygen because it will produce rust. Gold, platinum, iridium, they don't react with water or oxygen. If you just remember that the alkali metals, they will produce white or colorless ionic compounds. For example, sodium chloride, which is table salt, it is white. that is an ionic compound because it is made of sodium and chlorine. Transition compounds are colored. So, for example, so for example, copper sulfate. Copper sulfate will be blue, for example. So remember that transition compounds are colored, and alkali compounds are white or colorless. Now, transition metals can form more than one type of ion. So, for example, group 1 metals, they will make +1 ions. Group 2 metals will make +2 ions. But for the transition metals, iron can make iron 2 or iron 3. You can also have vanadium, manganese. They will make different type of ions. So if you look at this slide here, scandium it will make 3 plus. Vanadium, you can make 2 plus, 3 plus, 4 plus, or 5 plus ions. For chromium, it can be 2 plus, 3 plus, 4 plus, or 6 plus. For manganese, it can make 2 plus, 3 plus, 4 plus, 6 plus, and 7 plus. So for these transition metals, you can make a variety of ions compared to group 1 or group 2 metals. Alright, so how do metals react with water and dilute acids? Now, metals form positive ions in reactions. If you remember that group 1 and group 2 and all the transition metals, they are less than group 4. So they are on the left hand side of the periodic table. And because there are less electrons than number 4, because it has less than 4 electrons in the outer shell, they will usually form positive ions. So the more easily this happens, the more reactive the metal. A metal can react with water or dilute acid if it is more reactive than hydrogen. For example, calcium reacts with water and dilute acids, but copper does not. Metals react with water to produce a metal hydroxide and hydrogen. Metals react with acids to produce salt and hydrogen. So if you look at the bottom of the slide, just need to remember the general equation of the reaction between water and metal produces metal hydroxide and hydrogen gas. So let me just repeat, metal plus water produces metal hydroxide and hydrogen gas. And then metal plus acid will produce salt plus hydrogen gas. How do you know if something is more reactive? Well, the more reactive something is, the quicker the rate, the faster the rate of hydrogen is made. Also, if there is vigorous bubbling, it means it's more reactive. So if it's more reactive, there'll be more bubbling. Also, if there is a bigger rate, the faster the rate of temperature change. So, for example, if you've got a chemical reaction, okay, let's just say that you've got two chemical reactions. One chemical reaction, the temperature change is, let's just say, between 10 and 20. And then another one is between 10 and 30, but they took the same amount of time. So in this case, from 10 to 30, that will be more reactive. Alright, what are metal displacement reactions? So this is just like the halide, where the more reactive halogen, that will displace the less reactive halogen. In this case, a more reactive metal will displace a less reactive metal. So if you look at the chart, the reactivity series, potassium is more reactive, and then the least reactive is platinum. In this case, if you have copper plus silver nitrate, the copper will displace the silver. So copper plus silver nitrate will produce copper nitrate plus silver. So because copper is more reactive than silver, the copper will attach itself to the nitrate, and then the silver will be left behind. It will be precipitated out. And then just like the previous example with the oxidation and reduction, the copper, it will lose electrons, producing copper 2 plus and 2 electrons, and then the silver will gain electrons because it's already ionized. The silver is already ionized. Once it's gained an electron, it will become silver as a solid. Okay, so in this case, the iodine won't displace chlorine, the iodine won't displace the bromine because iodine is further down. The further down the halogen group, the less reactive it is. So therefore, iodine won't be able to displace the chlorine. Let's have a look at this question. So let me just read this out. So this test, let me just read at the beginning. Using silver nitrate solution. This test is carried out in a solution of halide ions. The solution is acidified by adding dilute nitric acid. The nitric acid reacts with and removes other ions that might also form precipitates with silver nitrate. Silver nitrate solution is then added and the halide can be identified from the following products. So once you've added the silver nitrate and you have no precipitate, that could be fluoride. If it's a white precipitate, it would be chloride. If it's a pale cream precipitate, it is bromide. Now, the word precipitate just means that when you have a chemical reaction, a solid is produced. And that solid is usually a salt, and that is called a precipitate. So if it's a pale cream precipitate, that will be bromide. If it's a pale yellow precipitate, that will be iodide. Okay, so this is the question. So you've got three aqueous solutions are sodium chloride, sodium iodide, and silver nitrate. They are in containers labeled X, Y, and Z. It is not known which solution is in each container. The solutions are mixed together as shown in the table, and the observations recorded. So, solution X added to solution Y gives you a yellow precipitate. Solution X added to solution Z gives you no change. Solution Y added to solution Z, there is a white precipitate formed. Explain how the results show that Y is aqueous silver nitrate. B. Explain how the results can be used to identify X and Z. Now, for part A, is more logic than scientific, but it is scientific, but it is more logic than scientific. B. Explain how the results can be used to identify both X and Z. Right, so the one that has no change is the second row. So the second row is where you have solution X added to solution Z, there is no change. For solution X added to solution Y, there is yellow precipitate. For the third row, it says solution Y added to solution Z, it is white precipitate. So what is the common factor? What is common in the first row and the third row? Well, the thing that's common is solution Y. So you can say that because the first row and the third row has solution Y in common, and there is nothing, there is no result in the second row because there is no Y involved in the second row because there's no change. That suggests that Y must be aqueous silver nitrate. And also because you need to add something to a solution in order for a change to occur. So in this case, Y is aqueous silver nitrate. I'll show you the mark scheme later on. Explain how the results can be used to identify both X and Z. Now, if it's yellow precipitate, it must be iodide. Yep, if it's pale yellow, it must be iodide. So if it's yellow, it's iodide. If it's white, it will be chloride. So white, it will be chloride. Right, so the mark scheme is here. So for A, because a precipitate was formed each time that Y was used. Or you can say that no precipitate was formed when X and Z were added together. I would have put two of them together. So in order for a logical conclusion, I would say both statements must be used. Except it reacts with X and Z to form a precipitate. So because when it says except it reacts with X and Z, that's because there's a common solution in the first row and the third row. And the mark scheme for the second part, X is sodium iodide, Z is sodium chloride because of the colored precipitate formed. Right, so these are the flame tests, and you see the colors. And this is from the C4 book OCR. So you only need to know lithium, sodium, potassium, calcium, and copper. For iron 2, iron 3 and zinc, there are no colored flame, meaning that there is no change. So, um, so the only distinctive color are groups 1 and 2, and one of the transition metals, and that one is copper. Right, so this is just a recap of the reaction of the alkali metals with water. So lithium, when lithium is added to water, lithium floats, it fizzes steadily and becomes smaller until it eventually disappears. For sodium, sodium is further down the alkali groups, so it is more reactive than lithium. The sodium melts to form a ball that moves around on the surface. It fizzes rapidly, and the hydrogen produced may burn with an orange flame before the sodium disappears. Potassium, again, potassium is more reactive than sodium and lithium. So when the potassium is added to water, the metal melts and floats. It moves around very quickly on the surface of the water. The hydrogen ignites instantly. The metal is also set on fire with sparks and a lilac flame. There is sometimes a small explosion at the end of a reaction. All right, so this is just a very quick summary of made it less. So you can have a look at this very quickly. Um, Right, I have tried to make a pattern, but there doesn't seem to be a pattern, but you can let me know. So for lithium and calcium, lithium makes a red colored flame, calcium makes an orange red flame, and I've circled it in the periodic table. For sodium is the yellow, and sodium is the one that's circled. For potassium is lilac, and then the one for the copper is in the middle of the transition metals. Sorry, it is just in the middle of the transition. It's in the middle of the periodic table. Um, okay, so for potassium is lilac, sodium is yellow, lithium is crimson, calcium is red, and copper is blue-green. Um, lithium. Okay, you can say lithium is just red. Calcium is orange-red. Red. All right, so see if you can fill in the gaps. Ignore barium. So what color is lithium? What color is sodium? What color is potassium, calcium, and copper? So these are the colors. Now, the only disadvantage of the flame test, it depends on the flame. It depends on the chemical used to produce the flame. So the fuel that's being burned. It's also very hard to match the colors with the charts with a high level of confidence. And this is another chart from a different website. So this one includes rubidium, cesium, strontium, and lead. Right, let's quickly talk about the instrumental methods of analysis. Describe the advantages of using scientific instruments to analyze substances, interpret results from an instrumental analysis. So what are the advantages? Well, if you have like a machine, a computer that can quickly do algorithms very quickly, you can say, yep, it is accurate because around the world they will calibrate these instruments. So there will be an international community. Again, it is very quick, and because you can turn it on and turn it off, you can run continuously if you want to. And because a machine is designed to analyze substances, it can be sensitive. There are expensive materials because it's very hard to get those materials. So because it's very expensive, you only need a small sample to be analyzed. And so that's the reason why for the machine to be sensitive, it is an advantage because you only need a small sample. Right, let's have a look at, so here you've got a chromatogram from a gas chromatography. So here you have, on the left-hand side, you've got hydrogen, oxygen, nitrogen, carbon monoxide, methane, and carbon dioxide. So here you've got 6 types of substances in this sample. On the right-hand side, you've got 4, and one of them is ethanol. So 3 are not ethanol. So if you look at point number 1, each peak is a different substance. Now, what does the peak represent? What does the detector response represent? Okay, so I've drawn an extra diagram on the bottom left. So let's just say that you've got in the substance, you've got these, what's another word for like parts? So in the substance, you have, let's just say in the substance, you've got two different chemicals. One chemical is, let's just say, is made up of 3 elements, and there are only 3 of them. And another substance is made of 2 elements, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 of them. And inside the chromatogram, the machine picks up a lot of these 9 molecules, and the machine only picks up 3 of the molecules made up of 3 elements. So that is what the peak represents. So if you have more of that substance inside that sample, it will have a higher peak, because the machine will register the higher amount of that particular substance. So let's just say the 2 element molecule is B and the 3 element molecule is A. The machine will pick up more of B and the machine will pick up less of A. Now the area under the graph tells you the relative amount. And the retention time, which is on the x-axis, it tells you how long that particular substance in that sample spends in the column. So for example, the longer the retention time, the longer it spends in the column, and that means it is attractive to the stationary phase. Because if it's not attractive, it will just go straight through the column. So if it's attractive to the stationary phase, it will stay longer in the column, therefore the retention time is longer. And if the retention time is shorter, that means it will just go straight through the column. It is not attracted to the stationary phase and it just goes straight through. Is seawater safe to drink? I wouldn't say so. There's a lot of salt in seawater. Rainwater is probably more safe to drink because in order to separate the salt from seawater, you need a lot of energy. Salt dissolves very easily in water, and the salt content in seawater is very high. Do fruits have salts? If we define salt as an ionic compound, then they probably have a low content of salts. However, fruits are acidic, so they do have a lot of H plus ions, and so they do have a lot of potassium ions. So for example, citrus fruits will have a lot of acid. 1 lemon could produce 0.7 volts, and yeah, so fruits do have high potassium levels, potassium ions, but they don't necessarily have a lot of salt, meaning ionic compounds.